So, there we go. All right. Thank you, everyone, for coming in. Today, I'm absolutely delighted to introduce Lori Porter. She is a NSF graduate fellow at the Columbia University, but before that, she was at my humble little institution at the University of Louisville, where we worked together on void galaxies. So I know Lori quite well. She is one of the best students I've ever had, and so it's incredibly nice to hear from her again and hear about galaxy quenching because that is a thing that we worked on together as well. So, Laurie, I'm delighted to hear from you again. So let's hear about your recent science. I'm excited.
Amazing. Yeah. So I'm super excited to talk about this. It's super timely. I actually thank you to Bene and Aaron for being very patient with me. I actually completely changed the topic I was going to talk about because I wanted to talk about this instead. The paper just went on published by AppJ just last month after probably like one of the best referee reports I've ever had. So very, very excited to do some discussion on this, especially in the context of habitable worlds and what are like the major outstanding problems that we're working on. So in brief, this is going to be physical views of galaxy quenching. And as a quick disclaimer, there's such a wealth of literature on this topic in so many works. So I'm going to not even brush the surface of it. But I think that's also one of the exciting part is that there's still so much discussion to be had on this topic. So to start off, I'm going to show you these overlapping pairs of galaxies. Clayton Robertson gave a really nice SIG on this almost a year and a half ago. But I really love this image because it really shows the fact that we see a diverse range of galaxies in the observable universe. And it also, like in one image, it shows us the galaxy bimodality. We see all kinds of galaxies, but for the most part, we can classify them, at least in terms of shape, into two different categories. We see generally like late type galaxies, or like very spiral, very disky galaxies, like the one on the left, or we can see more spheroidal galaxies like ellipticals or lenticulars on the right. And we usually refer to those as early type galaxies. It's not the most conventional naming mechanism. It's a little bit inverted, but it's really unique that these two galaxy populations are not just in morphology. So this is a color magnitude diagram that also shows the fact that these galaxy populations aren't just, it's not just the shape. We also see in magnitude and in the color. So generally, we call these two populations the red sequence and the blue cloud. So if we want to simplify this to just a couple of cartoons, generally we can say that these two populations also have their own distinct characteristics. So we also see like these correlated properties. We see the fact that these red sequence galaxies, or these early types, usually reside in denser environments. We see them in groups and we see them in clusters. We usually say that they're passive, so they have a lot less star formation, which in turn can cause the red color. They also tend to be older. And we also usually see that they have a lot less gas than these blue cloud galaxies. Then when we compare directly the star formation, as I mentioned that they're passive, we can say that the transition from the blue galaxies, which we call usually the star formation main sequence, we see when galaxies turn red, their star formation tends to drop. They become quiescent, and that drop is what we call galaxy quenching. And there's a lot of different pathways to quenching. And it's one of the biggest problems facing galaxy evolution. How do galaxies quench? Why do they quench? And what specific pathways are responsible for a variety of galaxy populations? We'll talk about that a little bit more later. Especially because I'm a graduate student. I'm of the opinion that every good science talk should include a meme. And this one's going to be a little bit more niche. So we have the illusion of free choice. But this is also a good way to think about galaxy quenching because there are two primary ways that you can quench a galaxy. You can go from, instead of, a cow deciding to go left or right, you can be a blue galaxy. In order to become quiescent, again, there's two main things that can happen. You can either reduce the amount of gas that the galaxy has. You can't make stars without fuel, or you can reduce the star formation efficiency. So you're reducing the rate at which that cool gas can form the stars. Maybe you can form stars, but you're only forming maybe like 1% of the gas into stars. So all quenching mechanisms have to take one of two paths. So I'm going to rewind a little bit. We talked about like blue and red galaxies. So when we see these ellipticals, especially in our intro astronomy classes, one of the main ways that we classify them is we say they're red and dead. It's very easy to remember. We usually say, oh, they have little gas. They've been stripped. But is that actually completely true? And increasing observations have shown that a lot of these early type galaxies actually have molecular gas reservoirs. So for a lot of these galaxies, it's not that they aren't not forming stars due to a lack of gas, or that's at least like what we can think. So this is a small population. So we've detected molecular gas in about 22% of our local early types. But what we also see in the survey from Atlas 3D and Massive is that, especially the more massive galaxies you get, the larger the gas reservoirs. So if these galaxies have the gas, why are they not forming stars? That allows us to somewhat narrow down and look into maybe like why some of these galaxies are quenching. So that means that we need to understand in galaxy evolution, why are these galaxies not forming stars despite having the gas? We can't simply say remove all of the gas from all galaxies and say we understand quenching. So what are the specific mechanisms to why a galaxy wouldn't form stars? So I love this diagram because it covers some of these main physical processes. And that involves gas inflow, gas cooling, and gas outflows, because star formation and quenching is inherently a baryon cycle problem. And we'll talk about that more later, but that's one of the great things about why habitable worlds is going to be so exciting. So one of the reasons is that maybe gas isn't accreting. So again, that falls into removing the gas from a galaxy. You can't form stars. Maybe you aren't receiving pristine material from the CGM. You run out of gas to form the stars. Maybe the gas isn't cooling. Maybe you have a hot halo and the accretion is hot, and the gas is unable to cool. But then maybe you have the cold gas doesn't form stars. You could have morphological quenching. There could be magnetic fields that are preventing it from the gas clouds from collapsing. You can also have the cold gas being rapidly consumed from, for example, mergers or disk instabilities, or you can remove the gas entirely through gas outflows. For example, AGN or stellar feedback, you could have super bubbles. You could have ram pressure stripping that just completely removes it. So I'm going to talk about one specific area, and that's going to be because we see again that these early types have the molecular gas. So why they're not forming stars? So I'm going to go over the idea of morphological quenching, and I want to note that I put this in quotes. The great thing is this is not necessarily a new idea, but it is important to go over the basic physics of it. So in general, morphological quenching refers to the phenomenon that when you have a galaxy that is dominated by the stellar bulge, it increases the central galactic potential. So when the central galactic potential increases, then you could also increase the angular velocity of the galaxy and the epicyclic frequency. So that causes the galaxy to become rotationally supported, and it stabilizes the galaxy against collapse for those gas clouds. This is usually represented in the form of the Turner Q parameter. So basically, this just says the numerator is the velocity dispersion and the epicyclic frequency. Those are the stabilizing forces. And then the denominator is the self-gravity. We have the surface density of the gas or the stars. So you can have this component in just the gas and describe that stability. You can use a more accurate two-component version. And when you do that, so even if you have like your gas disk, If Q star is too high, that can cause Q gas to also become high. And then generally we say that when Q is greater than 1, it's gravitationally supported and it's stable and star formation is suppressed. This is a very simplified version of the theory, but that's in general why we think that potential spheroids could suppress star formation. It's not that we're removing the gas. You can have the gas, but that spheroid reduces the dynamical importance of the gas disk's self-gravity. So you can still have this denominator, but the numerator, the stabilizing forces become so large that you just can't overcome the force of gravity. So what are potential evidence that we see for this theory? There's already been a lot of links between bulge-dominated galaxies and less efficient star formation. And this has also been shown for a long time. We also generally see that there's a correlation between quenching or a lack of star formation and stellar bulges in galaxies. So, but these are also, we know, these are correlations. It's hard to prove that it's directly causing it. But there's a lot of studies, for example, for like X gas and X cold gas. They suggest that this is the mechanism that could result in these bulge-dominated galaxies falling below the main sequence and the Kennicutt-Schmidt relation, which relates the surface density of star formation in gas, but also maintaining surface densities of cool gas that are similar to these like star forming spirals. Another example is from the Khalifa survey that directly looks at the impact of the gravitational potential and star formation. And this is just one plot where they show the circular velocity curves of different galaxies. And we can see in general, if a galaxy is retired or quiescent, we'd see like a much larger rotation curve than these star forming galaxies. So that's another potential example of how rotation can dominate a galaxy and suppress the star formation. But this is all just evidence. Fortunately, this is not solved. I still have a job and a thesis topic, but not everyone agrees. Not everyone sees this, which again is why it's a theory, and we're still studying quenching. Because morphological quenching isn't always observed in bulge-dominated galaxies. We have observations and we have simulations that show that you can have a bulge-dominated galaxy and star formation is either not suppressed or the star formation can be just as high. It could also be due to a lack of gas. We also come into the problem that a lot of galaxy properties are cross-correlated. Just because we see an increase or correlations between the bulge and star formation doesn't mean it has to be morphological quenching. There's other causes for this, including AGN, because we know that AGN and bulges also have correlations. So that means that we run into the problem of what is causing quenching and what is a consequence of quenching. And that's one of the main problems that we're studying. And there's a lot of issues that can go in this, especially the fact that some of these other quenching mechanisms can be very hard to study. So I want to go back to this diagram. Remember the two ways that you can reduce star formation. Reducing star formation efficiency looks like if this is happening in these early type galaxies, that would be the cause. So let's take a brief look and look at some star formation efficiency. So I hate showing equations in talks, but I'm going to show you this one because it's really important. Generally, the star formation efficiency is modeled by saying we have like some relationship between the efficiency per free fall time, the gas density, and then the free fall time. So all this is saying is if we allow a cloud to collapse for one free fall time, what fraction of the gas is becoming stars? Is it 1%? Is it 2%? Is it 100%? And in general, when we do cosmological simulations, we inject a constant star formation efficiency. To match observations, this is fixed at usually about 1%, and that's like a global value. We say it's usually uniform across the entire galaxy. But that's not always the case in a realistic universe and in a realistic galaxy. When we look at it on the cloud scale, where the star formation is actually happening, the efficiency is not constant. It really depends on the local state of the ISM. It depends on the turbulence. It depends on the gas. And there's a lot of studies that show globally on the galaxy scale, we can regulate the efficiency of star formation. We can get that efficiency of 1%. There's a reason we usually choose that value. But that's only if the efficiency of the galaxy is high enough and you have sufficient feedback. If you have a galaxy that doesn't have much supernova, there's not a lot of turbulence, or in general, there's not a lot of stellar feedback, it's a lot less likely for that efficiency to be regulated on the global scale. And that could be the case in a lot of quenched early type galaxies. So the star formation efficiency is likely really important. So here's an example of some recent simulation work that specifically tested the star formation efficiency in our subgrid models and simulations. So what they do is they use two models. They use a constant star formation efficiency of about 1%, as is commonly used and assumed. And they also use a star formation efficiency that is dependent on the dynamics of the gas. They take into account the Virial parameter, the Mach number of the gas. And what happens when we keep all of our other parameters the same, but that's the only thing that we're changing. And the results of this over cosmic time, as you can see, this is Mach images of the galaxy, face on and edge on. You get a really different galaxies when you change the star formation efficiency. So they say in the constant efficiency, you end up with a higher gas and baryon fraction, and you get a large gaseous and star-forming disk. But in the varying efficiency, when we take into account the dynamical state of the ISM, you get a more spherical galaxy with a really tiny nuclear gas disk. And the gas fraction also ends up a lot lower, and you get these dispersion-dominated systems. They also find that at late times in the constant efficiency model, the star formation increases with gas fraction. As you might expect, there's more gas available and therefore more stars. But again, in the dynamics dependent model, it doesn't, because it's a lot more dependent on the shear induced turbulence, which is nonlinear and a lot more difficult to model. So it looks like the subgrid physics, when we're simulating galaxies, really has an effect, which is good news and bad news for quenching, because in order to then study quenching in different galaxies, the way that you implement your star formation and in turn your feedback is going to affect what kind of quenching you see. And in a lot of these studies, we see that we need to consider the local state of the ISM if you want a quenched elliptical galaxy. So a similar study also tests the impact of the bulge. Is the bulge causing the quenching? Or can you get, an elliptical galaxy that has some star formation? And one of the benefits of the study by Yinja Gensier also includes the star formation efficiency models. They include one that is dynamics dependent on the Virial parameter, and they include one that is constant star formation efficiency also. So one of the great things is all of these galaxies are initialized with the same initial conditions. The only difference is the star formation prescriptions, and they also vary the bulge mass and the scale radius. Everything else is kept the same. So this is a version of the Kennecut-Schmidt plot that shows the surface density of star formation and the gas. These top panels are the constant efficiency model. We see that those follow along the main sequence pretty well. But when we consider a dynamical model on the bottom, it doesn't work quite as well. We're a lot more likely to fall below the main sequence of star-forming galaxies. And so on the left column are the bulgeless galaxies. Those are very disky, well along the relationship, as we might expect. They have a fiducial model and then a really compact bulge. So in general, what we see is that when we have the dynamical model of star formation and when we have a dominant bulge in the galaxy, you're a lot more likely to fall below the main sequence. You can still fall below the main sequence with the bulge if you use constant star formation efficiency, but the effect is a lot more pronounced when you're using a model that depends on the ISM. In general, they also find that when you include a bulge, you almost always increase the gas velocity dispersion, the virial parameter, and the turbulent pressure in the center, which means that the galaxy can then be supported against collapse through these shear velocities, which really tells us the impact that shear could potentially have on this star formation. And again, you can get these results using constant efficiency, but they're really only elevated to the levels that we can see in observations when you use a more dependent model. So again, here is the star forming main sequence. And these are very small points, so don't worry. I'll point out the important ones to you. But in general, this is where they vary the bulge mass and the scale radius. And what's really pronounced is in this little blue box, we have the most bulge-dominated galaxies. And those are with the dynamic dependent model. And those, again, are the ones that fall below the main sequence the most. Constant star formation efficiency and no bulge is right around the main sequence within the error bars. So if we go back to the theory of morphological quenching, when you hear morphological quenching, your first thought is, oh, it's dependent on the morphology. It's dependent on the bulge. And that is not necessarily untrue, but it also skips that crucial step, is that you need to increase the rotational support. So like these previous papers, I am now a little bit biased on this theory. And instead of calling it morphological quenching, I find I much prefer the term dynamical suppression, because that's the real physical cause of what's determining whether these gas clouds can collapse and form stars. Because again, you can have a bulge and not quench star formation. What really matters is the rotation and the galactic shear. So on that note, we've learned that your subgrid models can potentially really matter, and it can impact things. But one of the downsides to that is simulating these with effective resolution is very expensive. And it's not always completely feasible, especially if you want large samples of galaxies. We want to study tens of thousands, hundreds of thousand galaxies, not, four. But it's also just not computationally feasible to have these really, really high resolution models and also get the number counts that we need. So one of the goals of the Learning the Universe collaboration is to substitute the existing empirically calibrated models, for example, on Kennicutt-Schmidt, in cosmological simulations, with ones that are based on higher resolution simulations that are capturing the really small scale physics that we need to model things like quenching. And then the goal is to determine which processes can we model by this physically motivated theory, and which ones can't we? What are the outliers? And where do we need to modify the theory to determine what else needs to be modeled? So this led to the first suite of simulations that initially focused on testing the pressure-regulated feedback model theory by Eve Ostreiger and Chang-Gu Kim. Sarah Jefferson led these simulations that are extremely high resolution. So we're resolving down to 1 to 10 parsecs in the cool gas. We have a mass resolution of about 850 solar masses. For context, that's about an order of magnitude better gas cell resolution than the previous simulations I was just showing. But these are also hydrodynamical isolated galaxies. This is a test case. It's really important to note that these are not necessarily real galaxies. Or when I say real, I mean like we're not including the cosmological context. So to do this, there are several galaxies that are simulated. We're simulating 4 early type galaxies and 1 Milky Way-like galaxy. So this theory is all around the bulge and bulge-dominated galaxies. I'm going to keep the Milky Way in here for a disk galaxy comparison, just so we can see how the physics are differing here in these types of galaxies. But these early type galaxies are all directly sampled from observations from MASSIVE and ATLAS 3D. So for example, some of the initial conditions that we're sampling, we have the halo mass, we have gas fraction, the disk to bulge mass, the molecular disk radius. We want to make sure that what we're simulating is physically meaningful and it's coming from what we're already directly observing in the universe. So again, these are not completely like real. These are heavily idealized galaxies. We don't have a hot halo. We don't have a CGM. We also don't have black holes or aging in. So that can be a pro and that can be a con. So we're able to investigate potential quenching mechanisms without aging in. But we also know that these could also likely have a huge impact on what we're seeing. So the important thing is to note all of these initial conditions are sampled as evenly as possible in this parameter space of the observations. We're keeping the same disk to bulge mass, but these are all like bulge-dominated galaxies. We also include, as we just saw, to recover some of these quenching mechanisms, we need star formation that is dependent on the local ISM. So we've already seen star formation volume density. That should be old news to you guys. But what's really important is the star formation efficiency here. We don't take into account the Mach number, but rather like the simulations of Genser, these are dependent on the virial parameter. This is how that's calculated, but that isn't particularly useful here. So what I want you to keep in mind is that this is basically just supposed to represent the ratio of the internal kinetic energy of a cloud to the self-gravitational binding energy. So what is kinetic energy to self-gravity? If it's above some threshold, gravity wins, and we should be able to form stars. So if this is really high, then we can directly impact the efficiency of that star formation. So these are what our simulations actually look like. We have this, we're going to label these for the early types in terms of stellar mass up at the top. The kind of like blue-white component is the gas, and the orange-yellow is the stars. So we see with all of these early type galaxies, there's, as we put into the initial conditions, a really strong bulge component. But what's really weird is how smooth some of these gas disks are, especially this 10 to the 11 mass galaxy. Despite the fact that it has like a higher stellar mass, the gas mass doesn't exactly correlate with that. And the gas disk is also much more compact, both face on, and we have a thinner gas disk edge on. So when we look at the star formation rates of these galaxies, this is comparing to some of the Khalifa galaxies where we have the star forming main sequence and the red galaxy sequence. Our early type galaxies are somewhere around the red sequence. The Milky Way is right around the main sequence, as we would expect. But again, there are 10 to the 11 solar mass early type galaxy is even below the red sequence. And it has a really, really low star formation. It's like 0.01 solar masses per year or less. And it also has the lowest specific star formation rate. So one of the really interesting things that we wanted to investigate, if these are all sampled and evenly spaced from the observations, why is the star formation rate so low in this one particular galaxy? What's physically causing this? So one of the first things is because these are bulge-dominated galaxies in line with the theory, we want to look at the rotation. Is it rotationally supported? So one of the first things is the central stellar density, which is labeled here underneath the stellar mass. This galaxy is much more centrally compact. It's 70% higher than the next galaxy, which is the 10 to the 10.5 solar mass. And then from the color correlations here at the bottom, we see that the circular velocity, the epicyclic frequency, and the angular velocity are also much higher. So that pretty much matches what we've seen in the morphological quenching or dynamical suppression theory. Rotation's stronger, but is it causing it, or is it just correlated? And how do we know? So again, here's the tumor Q parameter. So we have the modified tumor Qs, for example, developed by Alessandro Romeo, that are supposed to represent more realistic galaxies. And in general, what we find is that it's elevated for all of the early type galaxies. It's a little bit more elevated for the really suppressed one, but not enough to make us immediately go, aha, what's going on here? Especially because in this bottom plot, so the gas is this dashed line here at the middle bottom panel. The velocity dispersion is actually lower in this galaxy, which is the opposite of kind of what is expected from a lot of these other simulations in the theory. We would expect that the velocity dispersion would be a lot higher as turbulence is supporting against the collapse of star formation. So we think that this could be feedback related. We also find that this galaxy has the lowest levels of supernova clustering, which means that outflows are a lot less efficient and it's harder for them to drive stronger turbulence in the galaxy. And you'll remember that from the 2-mercute parameter, if you have an elevated epicyclic frequency, but not velocity dispersion, you can still have the high 2-mercute. But if velocity dispersion is lower, again, what exactly is driving the star formation suppression in this galaxy? And how do we go about that in a more physical way? So if we assume that the external potential matters, that star formation does not occur in singular isolated clouds, what forces are acting in a gas cloud? So this is motivated by some of the wisdom survey where they can resolve individual molecular clouds and GMCs. And this theory actually comes from there and work by shear and White. And I really prefer this. I really enjoyed this because it reminds me of going back to physics 101, drawing your free body diagram and what are the forces that are acting within, what's responsible. So a lot of this, you start with a modified version of the virial theorem that's dependent on the moment of inertia of your cloud, the kinetic energy, and then you have of the volume integral over the overdensity. That's a little scary. That doesn't look very easy to calculate anything from. So here's a much more familiar version. So this is basically just a typical virial theorem where this 0 represents the condition required for collapse. We have our total kinetic energy, self-gravity, and this is the midplane term from the external gravitational potential and from perpendicular to the midplane. So what actually comprises? We can say, oh, gravitational potential in the midplane, but what does that mean? So this basically results in 3 primary forces. We have the Coriolis force, we have tidal forces, and the centrifugal force. But because I'm a theorist and we love to approximate things, we're just going to completely ignore the forces perpendicular to the midplane, so in the z direction, because the gas disk is mostly symmetric, and when testing this, it's about 0. It has no real effect on everything. And because we have circular motion of clouds in the galaxies due to the rotation, the tidal forces and the centrifugal force just about cancel out. Together, those contributions are almost exactly 0 because they're axisymmetric. So that means we can go from this little more scary looking form up top to a much more physical form at the bottom. What really matters to collapse a gas cloud is the kinetic energy, the self-gravity, and the Coriolis force. So when we actually look at this in our overdensities in the simulations, this is just the median over all overdensities. This is what we find in terms of these energies. The kinetic energy appears to just about scale with the stellar mass. So we have more stellar mass, there's more kinetic energy. But the self-gravity does not scale. The self-gravity, even though is actually larger in some of our smaller early type galaxies than in the suppressed 10 to the 11 galaxy. And that's not necessarily because it has less gas mass. Again, from the contribution of the stellar potential, it just decreases the relevance of that gas surface density. And of course, the one that stands out is the last panel, the Coriolis force. It is significantly elevated in that suppressed galaxy. The Milky Way, like disk galaxy, experiences almost none whatsoever. But that's really the thing that stands out about this galaxy compared to the others, is that the energies from the Coriolis force appear to be dominating in that suppressed galaxy. But also the relevance of the self-gravity shouldn't be neglected. So the efficiency of star formation, I've been talking about that a lot. If it's set by the virial parameter, and I told you that the virial parameter is the ratio of the kinetic energies to self-gravity. If the Coriolis force is responsible for suppressing the star formation, would we not see that in a relationship with the virial parameter? And the answer to that is we do, which is one of the key reasons why we think this is what's suppressing it. We see that a lot of the early type galaxies, except for the suppressed one, follow a very similar relationship. As the Coriolis force increases, so does the virial parameter. But as you go to low virial parameters and therefore low Coriolis forces, you have a lot higher star formation efficiency. That's the color bar. So as it gets more yellow, it's a lot more efficient. And you don't really see that in the suppressed galaxy. We don't have those higher star formation efficiencies. Again, in the Milky Way like galaxy, almost no correlation whatsoever because the Coriolis force just isn't as relevant there. But again, I mentioned that the equation for the virial parameter should represent the kinetic energy and the self-gravity. That's not, the Coriolis force isn't implemented into the simulations in the classical virial parameter. We're not directly taking that into account when we're modeling star formation. So how could that have an effect? And the answer is in the rotation and the shear induced by it. So this bar plot is similar. So that's the fraction of rotational kinetic energy towards the total midplane kinetic energy. So basically, is rotation dominating the total kinetic energy? And the answer is yes, much more so for that suppressed galaxy in pink. So we can still have turbulent kinetic energy, but the rotation is just so much stronger in that suppressed galaxy where we see the high Coriolis forces. And that's really important because even if you're not directly including it or accounting for it, you can still end up seeing the importance of the galactic rotation and the Coriolis force in your kinetic energy budget. So again, even when it's not accounted for, it can still show up, but really we probably should be accounting for it in some of these simulations where it appears to be relevant. But on that note, there's also a lot of caveats to what I just described, especially like as a theorist. Star formation is messy. Star formation doesn't occur in these single clouds. It depends on your models. Even our observations differ. What signatures are we detecting? How accurate are those signatures? So we need to understand star formation. And real galaxies are not idealized like this one. Galaxies have a CJM. Galaxies have mergers. They have black holes. So we also need to take into account the fact that the effect that we see is occurring in these super, super idealized galaxies. And I think that this quote from a 2017 paper by Rebecca Smethurst is extremely relevant in terms of quenching. That multiple quenching mechanisms will affect galaxies across their lifetime, and that they likely work in collaboration to ensure the galaxies stay quenched. So that's another reason I prefer to move from morphological quenching to dynamical suppression. Just because a galaxy isn't completely quenched does not mean that dynamics don't have an effect on the star formation. So when we say quenching, we should also be careful about what we're referring to. More of a language thing, but just because maybe it's not the sole reason for galaxies having little star formation doesn't mean it doesn't have an effect. But with that means that there's still so many questions. Again, I still have a job. There's so many things that we still need to look at and we need to answer. What does it take to rejuvenate star formation? For example, in our suppressed galaxy, if we suddenly started feeding it pristine material, would that cause it to overcome the rotation? That's observed in the original theory, but would we find that also with our higher resolution simulations? There's also supposedly a dependence on gas fraction. We have very low gas fractions. That's where morphological quenching is supposed to be most effective. But what about the central stellar density? How does this change with redshift? What about our high redshift galaxies? Can we develop a specific threshold, preferably in observable quantities? How do things change again when we consider realistic galaxy conditions? Can we apply this to some of the observed galaxies in Atlas 3D or Massive using their parameters? Is this applicable to regions where rotation may dominate, like the central molecular zone? or post-starburst galaxies? Do we need the bulge if we have the dynamics to suppress star formation, especially since post-starburst galaxies are almost an order of magnitude more compact than the ellipticals that we simulate here? And again, one of the most important ones is, how does this couple with other quenching mechanisms? Does this work with AGN? Is it overcome? How does it work with mergers? So how do we quench these suspicions about star formation with habitable worlds? Pun intended. So again, this is inherently a baryon cycle problem. We have to understand star formation. We have to understand gas and what the gas is doing. And all of these are just assumptions, but we really need to understand to the fullest extent possible. I haven't talked about feedback a lot, but it's also equally important to what we're seeing. And that's why habitable worlds is really going to be revolutionary for studying quenching. If you think the archive is overwhelming with JWST results, that has the potential to be done again with such an observatory. So these are three of the questions I'm most excited about that habitable worlds could answer. And that's, how do morphological components regulate local star formation? And that could come from the stellar age gradients with the UV star formation maps across different galaxy substructures. Kartik Iyer gave a really great SIG talk and had a similar mention in his questions. For example, are quenched galaxies really gas poor? So we see some molecular gas. What about the diffuse gas? What about the hot gas? What about the potential for that to cool and fuel future star formation? But we need to detect the hot gas to do that. That's extremely hard, but could be possible with HWO. And again, I'm also like, I have a special place for feedback in my heart. So how do feedback driven outflows connect with long-term quenching? And how do they evolve over cosmic time? For example, when we look at super bubbles, when we look at the strongest winds driven by stellar feedback, we really need to observe these outflows. We need to observe them across galaxy types, and we need to see how they affect the galaxies at large. So I will leave my primary conclusions up. Really, what we studied is that so star formation is not simple. Star formation requires us to understand the baryon cycle, the galaxy dynamics, and we think that the gravitational potential has a real impact on all of these things in certain galaxy populations. More compact galaxies show evidence that shear and rotation can suppress their star formation. Again, but only in certain galaxies. We still need to develop a threshold as to at what point is this super relevant versus when is it overcome potentially by other mechanisms. But in some cases, it's not negligible, and you need to take into account. But habitable worlds also has the potential to answer a lot of these questions and more. This is just, I wanted to pick my three favorites. But all of these talks have given some amazing insight into all of the things that we could discover and elaborate on with habitable worlds.
That's excellent. Sorry, I need to find the clappy emoji quickly enough. Yeah, so opening it up to the room. I'm not the simulator in the room. That would be Aaron and maybe some other people. So who has questions? Time to jump in. I always do. So I will wait until the room has had a chance to ask their questions or suggestions, ideas.
Anyone? A quick one. What's your most exciting next step?
Ooh, okay, great question. And that is also that's one of my questions as well. That's why my questions slide had so much text on it. I think right now it's determining how do we observe this? How do we observe the Coriolis effect and the rotation in some of these galaxies? How does that? Yeah, not an immediate answer. So can we come up with proxies for that? Or can we at least develop some sort of threshold in observational parameters? But I'm also looking forward to investigating the potential effects of resolution. So in some of our other simulations, what's the resolution level needed if we want to look at the impact of galactic shear on the gas? So they're just those are two things I'm currently working on and thinking about.
Yeah, this is sort of one of the million-dollar questions that I worked as a simulator for years and tried to integrate myself into the observing community. What can we see? How can we
Yeah.
test this? That sort of thing. So yeah, as you know, as you progress with this project, it's always nice to also on the side think about what aspect of these simulations can be translated into observables that can be used to motivate future surveys or even a new telescope.
Exactly. I gave a similar version of this talk in March at a Quenching conference that mostly focused on post starburst galaxies, and that was super exciting to me, and I think is a really promising next step is because these are really gas rich galaxies, but they're really compact and they're not forming a lot of stars. So is this relevant? And that was the most common question I got is we were at lunch sketching out diagrams on napkins of what can we observe and how can we relate that to the simulations and predict these things, like especially like in velocity space of the gas. Because one of my main goals is I don't want to be a theorist that is presenting these things that could be important, but then giving observers absolutely no way to test the theory whatsoever. So I think that really is like the most important next step.
Great. Sounds like a seminal paper in brewing.
Uh, I have a question, of course, and that's the dynamical suppression one. Shear is sort of invoked a lot for low surface brightness disk
Mhm.
galaxies as well. So that would be, but they're famously not compact. But for elliptical galaxies, so ETGs, there are some really compact galaxies found at like redshift 3, 4. And they're massive. And so the question is, well, this is the height of star formation. Why aren't they making any stars? So this would be a good example to compare to. Of course, redshift, 2, 3, 4 is terrible to get any kinematics, but you can imagine comparing your central density with it, your morphology, stellar mass, that like looking like, hey, this could be the explanation for it's a rare class, but basically they're not seen locally anymore. They're so
Mhm.
dense that they're not. So what happens to them? And I think that was people sort of looked at the um, what happens to them kinematically, and they sort of spread out later. But it would be interesting to see, like, hey, is this the reason that they're not forming stars anymore? Like right after a starburst stopped doing anything. So the question was like, is that something that could you compare the central densities of the 10 to the 11 like the 2011 sort of tweak that your central densities to observed central densities of ETGs because that was a hot topic for a little while for in ETG world.
Yeah, that's one of the things on my wish list of what I'd like to accomplish during my PhD. So emphasis on wish list because like it does have the potential to be an impact at high redshift. Um, it's one of the things I would like to do, but it does become hard when we only have one simulation of where this is especially relevant. I'd really like to have a couple more, at least so we have a variety of stellar masses, a variety of different properties to compare before we do that. But it is a really promising next step.
Adam Muzzin, sorry, I was looking for the name. Yeah, Adam been looking at those ellipticals, and I was like, it's Adam. What was his last name again? So yeah, you want to look at some of the Muzzin papers on that as well. I'm gonna be quiet for a moment and see if anybody else has a question in the last 10 minutes. Otherwise, I'll have another one. I'm sure I do. Okay, I counted to 10, which makes it premeditated. Uh, for disk galaxies, so the sort of the other end, right? This is where this becomes important too. I just refer to the low surface brightness component, but even within disk galaxies themselves, you can imagine Q sort of changing as you go
Mhm.
from small disk galaxies to bigger disk galaxies. There was a whole thing in a paper by Daniela Breshkov about the size of the bulge to total ratio, and then the relation with total angular momentum and baryonic mass. So this was a here's a fundamental plane for spiral galaxies.
Mhm.
So I'm curious about sort of expanding this how important shear is, how important the stability is into disk galaxies, because basically how much of does that bulge play a role? And we'll have this at scale, right? We'll have bulge to total ratio to scale. We'll have rotation curves to scale because H1 surveys are finally taken off. So um, you could say, hey, this is the star formation efficiency I'm expecting based on disks as I go through the main sequence, right? So main sequence star formation efficiency should change from like high end, should be low. I think it's low, but basically the Q parameter for those are less than one. So basically everything sinks to the center. And then in smaller galaxies, you expect that to be lower because basically the clouds don't fall into that disk. So that would be another way to expand this. Like you already have a Milky Way one, you can just add a couple at lower masses. So basically add a couple of like a LMC and a SMC one, and look at the star formation efficiencies there because we sort of expect that to change with the main sequence. Is that one of the
Right.
plans? I mean, I can give you more stuff to do in your last 2 years of grad school. Ah, there's a question. Excellent. I knew if I talked long enough, somebody would go like, "No, I have an opinion." One, what's
Hi. Hi, Laurie. Really nice work. Um, I have a somewhat naive question. So, a lot of people like to compare with the Koenig-Schmidt law, and I'm wondering if you've done it, and if, more specifically, have you looked at the sort of spatially resolved Koenig-Schmidt? Because if you're arguing that it's the central compactness that's making things different, maybe even within one galaxy, you would see different, I don't know, relations.
Yes, so that was done in the original simulation
Oh.
paper by Sarah Jefferson. She compares how these galaxies fall along the Koenig-Schmidt law
Hmm.
in terms of, so we look at total gas, the molecular gas, and then also the molecular and atomic gas contents. And in general, like we find that like the more suppressed galaxy does, it maintains the similar gas densities. But it's just the star formation that falls that makes it fall below Kennicutt-Schmidt. And then they have a section where they compare the efficacy of Kennicutt-Schmidt to the pressure regulated feedback model. And they find that generally like that's a better predictor than Kennicutt-Schmidt. But the suppressed galaxy still isn't described well by PRFM. So that's done a lot in the original paper. I just only so many slides.
Okay, thank you.
okay? I have a minute left, so I'm just going to jump in unless anybody has one. Um, so I'm still intrigued by the suppressing star formation as the bigger galaxies, right? Um, So that's sort of an elliptical galaxy that has gone through the Green Valley, but you would expect some morphological features more in the Green Valley as a result of like that's actively undergoing suppression. Um, how do rings sit in the shear rotation suppression? Like, where does that sit in the morphological features here? Because, like, again, you said like not morphological quenching, but rotational quenching, which I think is a better term. But I always wondered about rings. They're more prevalent in the Green Valley. Is that a chicken or an egg problem? Is that do we start seeing them because the star formation goes down, or do they appear and that makes the star formation become less prevalent? So would this be something that
Great
you
question.
Yeah.
I wish I knew the answer. Because I do think that that goes into of what causes quenching versus like what is a consequence of quenching, especially as we go like through the Green Valley and from the main sequence. We don't see like really strong signs of any of those in these simulations, but again, whopping sample size of 4 for the early types. I know Vasilina Kalinova has a great paper. So I showed her circular velocity curves. But she also goes through and she specifically identifies some of the rings and where those fall and how it relates to like the gravitational potential and the shear. I don't know if it's really been done in a lot of simulations.
There's always open questions with quenching. So this is where, yeah, I think it's sorry, the talk also reminded me of the manifold ideas for this star formation stellar mass. Like, did you sort of actually move on sort of like this multi-dimensional plane? So that's something a way that observers have tried to quantify this stuff. But yeah, if you put a galaxy's a big rug. If you pull any thread, you pull all the threads. So I really, yeah, nice job on the paper. Well done. So
Thank you. Thank you.
yeah, what's next? Let's, yeah, we asked that already. Okay, any other questions? We have a minute left. Please jump in. No, Aaron?
I'll just quickly say that let's wrap this up. And this is our last talk before the summer. So we'll come back in the fall and bring you a new seminar series. And of course, John and Benny and hopefully a few new recruits will be able to tap into a range of equally excellent speakers. But I won't be around anymore at that time because I'm like 12 hours behind or ahead.
Ooh, well,
it's like bad time for me.
Aaron's going on a new adventure in Taiwan, so that's going to be he's going to be a faculty member.
Yay!
The joys of being a professor. So that's so good.
Of course, if any of you happen to be in Asia and want to add a stop in Taipei and Hsinchu City, where I will be at, just drop me an email. We'll be happy to host all of you. All right, everyone, take care.
I'll see you. Thank you, Laurie. Thank you so much.
Thanks for having me.
Absolutely. I'll hope to see you in the world.
Thanks.